I'm Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. Today, in this video, I'm going to discuss about one of the optoelectronic device. Of course, this device it is made up of very important materials called as semiconductors. So, and that particular optoelectronic device which we are going to discuss today is solar cell. So, I think nowadays everywhere, even for household applications, also we are using a solar panel so that we can get our current from abundant of solar energy available from our sunlight. So today we are going to see what exactly the solar cells are made up of. Okay, and when we just see the solar modules which are installed in our homes or companies or offices, they are just not just made up of one single solar cell, but they are made up of bundles of solar cells. So, what is the construction or what is the material used in order to make each solar cell unit of a solar module that we are going to discuss? And apart from that, what exactly happens and how we are going to generate electricity from solar energy, that process also we are going to discuss today. So, starting about this solar cell, as I told you, this solar cell, it comes under the category of optoelectronic device. So this particular solar cell, it comes under the category of optoelectronic device. And what exactly are optoelectronic devices? So these optoelectronic devices, they are going to convert either light energy to electrical energy, or they are going to convert electrical energy to light energy. So in our solar cell, so it will come under where we are going to give our input, which is in the form of light. Of course, this light is our sunlight, as I told you, which is abundant in nature. By making use of that solar energy, we are going to get our current. So here there is conversion of light energy to electrical energy. And generally, when we talk about basic principle behind the functioning of a solar cell, we'll say that this solar cell, it is also called as photovoltaic cell. So these solar cells, they are also called as photovoltaic cell. And as you can see here, so now here when we talk about optoelectronic device, optoelectronic cell or photovoltaic cell, so what exactly is the difference? See, already in my previous videos, I have discussed about one more optoelectronic devices, which is in which is very much closer to the solar cell. The device is nothing but our photodiode, and in this photodiode also. So when we try to represent our photodiode, we are making use of symbol of diode, and here we'll put. So we have a diode, and what is the input energy? Here input energy is our light energy, and then our output energy is electrical energy. So here also there is a conversion of light energy to electrical energy, and basically what we are going to do here, light energy to electrical energy conversion will be there. And when we talk about this photodiode, we have taken a reverse bias diode. So what is reverse biasing? Where we'll take our PN junction, and in PN junction, of course, we have this junction there separating both P-type and N-type semiconductors. And in P-type semiconductors, we have majority charge carriers holes. And in N-type semiconductors, we have majority charge carriers electrons. And we know that when we reverse bias a PN junction, where P-type of PN junction is connected to negative terminal of battery, and N-type of PN junction it is connected to positive terminal of battery. We know that these holes, because these are positively charged, they get attracted towards the negative terminal of battery, and similarly these electrons which are positively charged, they get attracted towards the positive terminal of the battery. And because of this attraction, what we are going to observe here is depletion layer. It is going to increase, and because increase of depletion layer is nothing but where we are going to have a lot of immobile charge carriers. And because there is increase in immobile charge carriers, so that's why current flowing across reverse bias PN junction diode is very, very negligible. And whatever small current we are going to get, that is leakage current, that is completely due to minority charge carriers. So, and in photodiode, what exactly we have done? So, we know that when we reverse bias a PN junction, and when we talk about VI characteristics of PN junction, we have seen that here first there is very small current flowing, right? Here we have taken our reverse voltage, and this is our reverse current, which is measured in microamps. So there is very small leakage current flowing across the PN junction diode. Now, our whole and sole intention in photodiode is to increase that leakage current. So for that, what we are going to do? So for that, we are exposing this depletion layer to light. So here we are exposing it to light radiation, and that light radiation, it can be of different frequency. So here we can make use of wide spectral response, where we are going to make use of different frequencies of light radiation. So they can be infrared, they can be ultraviolet. So depending upon what type of light radiation we are using, so based on that, your this reverse current or photo current, it is going to intensity of photo current, it is going to change. So in talking about this photodiode, so when we expose a depletion layer which is wide, when we reverse bias the PN junction, then whatever photons are present in this light radiation, these photons, they are going to penetrate into this depletion layer, and they are going to collide with immobile charge carriers. So here they are going to collide with immobile charge carriers. They will give their energy to those immobile charge carriers, and they will generate electron hole pairs. So there will be generation of electron hole pairs, and because of generation of electron hole pairs, we'll observe that there will be increase in photocurrent. And when we try to consider VI characteristics of a photodiode, what we have observed here is, as of course, when there is no light being incident on depletion layer, whatever current is being whatever current is flowing across the diode, that is called as dark current. And what we are going to observe here is, depending upon the intensity of light that is falling on this depletion layer, this leakage current, it is going to increase. So here we can have different intensities of light intensity. Suppose it is it has got this 2 luminous intensity, then it is 4, then it is 6. So as we keep on increasing intensity of light, our photocurrent is going to increase. Now, when I talk about the solar cell, why I have to talk about this photodiode? Because in most of the comparison way, the solar cell functioning, it is just like our photodiode. But in photodiode, we are making use of our high frequency radiations. But in case of solar cell, we are going to make use of solar light. And second most important point is, of course, here we are reverse biasing. Here, in case of the solar cell, there is no application of biasing voltage. So no biasing voltage we are going to apply in case of solar cell. And materials used to make photodiode, there are normal semiconductor diodes like silicon and germanium. Whereas in order to make solar cell, we'll be making use of some special type of materials that also we are going to see in this video. So, and when we talk about solar cell, here completely we are saying that its functioning, it is based on the phenomena, and that phenomena, it is called as photovoltaic effect. So that phenomena, it is called as photovoltaic effect. So what is photo? When once we make a light to fall on the solar cell, there is generation of voltage, okay, across the junction. And because of generation of that voltage across the junction, there will be flow of current. Okay, and of course, as I told you, it will come under optoelectronic device, where there is conversion of light energy into electrical energy. And basically, as I told you, these solar cells, they are called as photovoltaic cell. And of course, these solar cell, they will just behave as normal PN junction diode, but only thing is, we'll be making use of some special type of materials in order to make use of this solar cell. And coming to this symbol of solar cell, as we have discussed about different optoelectronic devices, when we talk about our normal PN junction diode, generally what we'll do, we'll take a triangle followed by a vertical line. This is our normal junction diode. This is the symbol of normal junction diode. And whereas when we talk about light emitting diode, so what we are going to do, we are going to take symbol of diode, and then we are going to show arrows going outside, indicating that this diode is emitting light. And in this case, this diode, what it is going to do, its input energy is electrical energy, which is forward biasing, and output energies are light energy. And this is the symbol for LED. Whereas when we talk about photodiode, in photodiode, symbol is completely different. So in this we are going to put our arrows going inside. So it means that our input energy is light energy and output energy is current. So this is the symbol for photodiode. So we have taken different, of course, symbols for different types of diodes, and I think also we have taken one more special type of diode, which is xenodiode. And this photodiode, xenodiode, they talk about increasing reverse current. Main basic principle is, main intention is, in order to increase reverse current when a diode is reverse biased. So when we talk about xenodiode, here xenodiode is also a reverse biased diode. And here in this case, we try to increase reverse current by heavily doping p-type and n-type semiconductors which are used to make xenodiode. So when we talk about this xenodiode, it is made with normal semiconductors, but of course, photodiode is also made with normal semiconductors. In photodiode, what we are going to do, extra light energy we are going to take, but whereas in xenodiode, we are going to make use of p-type and n-type semiconductors which are heavily doped. And talking about a symbol of this xenodiode, so the symbol, it is taken like this. So this is the symbol for xenodiode. Now coming to our solar cell, which we are going to discuss today. And this solar cell symbol, as we can make out here. So here we have, of course, positive terminal and then negative terminal. And what is the input given? Input given is our solar light. So this is our solar light, okay, which is made to fall on a PN junction diode. And here that PN junction diode, it is represented like this, where this is positive terminal and this is negative terminal, or also we can say that this is anode end and this one is cathode end. So this is the symbol of solar cell. Then moving further, first we try to see what is the construction of the solar cell. Now, talking about construction of a solar cell, as we have seen that a solar cell, it is just like our normal PN junction diode. So, it also consists of N-type and P-type semiconductor material. And when we talk about their doping, now as I told you, in the when we have discussed about xenodiode, in xenodiode, both P-type and N-type semiconductors are heavily doped. But when we talk about a solar cell, what we are going to observe here is N-type is highly doped, whereas P-type is lightly doped. So we are maintaining N-type semiconductor highly doped. It means that here we are going to add lot of pentavalent impurities. But whereas when we talk about this p-type semiconductor, there will be small amount of travalent impurities being added. So in this way, it is different from xenodiode. And of course, what we are going to do here is, in this particular thing, we are going to make top and bottom layers of this PN junction diode conductive. And in order to make it conductive, we'll have a coating of electrodes. So what we are doing, top and bottom, it is made conductive, so that there will be flow of current in the circuit. And generally what we'll do, bottom surface, in bottom surface, if we look at this figure, so in this figure, as we can make out that this one, so this top layer is our N-type, which is heavily doped. So this N-type silicon, here it is heavily doped. It means that we are going to add lot of pentavalent impurities. Whereas, as you can see, this bottom layer is a p-type silicon, which is lightly doped. And this N-type silicon, heavily doped N-type silicon and lightly doped p-type silicon, of course, they have this junction layer, and this junction layer, it is called as depletion layer. And we know that in depletion layer, we have lot of immobile charge carriers. And next thing is, what we are going to do is, in order to get our output energy, which is our current, so we are going to arrange electrodes on top surface as well as bottom surface. So first of all, what we are doing, this bottom surface, it is fully covered with conductive layer. Okay, so this bottom surface, as we can make out, this is the substrate base, and it is fully covered with conductive layer. Whereas this top surface, so it is not fully covered. As you can make out that we have left some area open, so that sunlight will fall on this PN junction in order to have penetration of solar light into the depletion layer. So what we are going to do, top layer, it is not fully covered, but it is a little bit left open, so that the sun rays can easily enter the depletion layer, which is present inside this PN junction diode. And what we are going to, of course, we know that since semiconductors are reflective in nature, we have to go for even anti-reflective coating, because our whole and sole intention is penetration of sunlight into the depletion layer. So that's why what we have to do, apart from just conductive coating, what we have to do, we have to go for this anti-reflective coating also, so that whatever sunlight is made to fall on this PN junction diode, it can enter, so it won't get reflected back. And what we are going to do here is this whole arrangement. So what is our whole arrangement? Here we have, of course, our PN junction diode, where N type it is heavily doped and P type is lightly doped, and of course bottom layer fully covered with conducting layer and the top layer. Okay, so it is partly covered with conducting layer, and apart from that we are going for anti-reflective coating, and this whole system we are going to keep it in a thin glass box. We can also call it as a box which is made up of thin glass, so that we can avoid mechanical shock. So this is the construction of solar cell. So as we can see that this whole arrangement, that's why we are using our symbol like this. So as we can make out that this whole PN junction diode, it is covered in a thin glass, so that we can avoid mechanical shocks. So this is about the construction, and as you can see in this figure which is given in the PPT, the solar cell unit, it is of course it is connected in a circuit, and in this circuit, as we can make out that there is 1 voltmeter. So this particular arrangement is to collect current that is being generated from this unit of solar cell. Now next is talking about the working of solar cell. So as we know that solar cell, working of solar cell, it is completely based on photovoltaic effect. So what is photovoltaic effect? This is nothing but generation of electric field or generation of depletion layer in generation of voltage in depletion layer because of solar light incident on depletion layer. That is nothing but photovoltaic effect, or simply we can say that here it is the effect in which current or voltage is being generated when exposed to light. So generally what is happening here, current or voltage is being generated when we expose our solar cell to sunlight. So our input is sunlight, which is different from our photodiode, where input is our normal high frequency radiation. And what we can say here is the solar cell, generally they are going to convert sunlight. As I told you, it is abundant in nature, and we can make use of this sunlight in order to get current. Okay, so that's why there is conversion of sunlight into electrical energy. Now, what basically is going for this conversion of sunlight into electrical energy? Now, if you look at this figure, which is given in this PPT, so here, as you can see, top I have N-type silicon, and what we have done, we made it in such a way that it has got lot of electrons. Why? Because we are adding lot of impurities. Our N-type semiconductor is heavily doped. So as we know that when we take intrinsic semiconductor, suppose I have taken intrinsic semiconductor silicon, and to that if I add suppose 1 pentavalent impurity in order to make N-type semiconductor, suppose if I have added phosphorus, we know that when we add phosphorus to intrinsic semiconductor, which has got 5 valence electrons, so out of those 5 valence electrons, it will form 4 covalent bonds with adjacent silicon atoms, and this 5th electron, it is free and it is going to take part in conduction. And when we say that our N-type semiconductor is heavily doped, so we are going to have many such electrons. Now next thing is we have to supply energy so that we can make these electrons move and they can give rise to current. So as you can see here in this N-type semiconductor, and of course below we have P-type semiconductor, and here what we are doing, we are going for light doping so that there are very few number of holes available. And of course this is our depletion layer. We know that depletion layer is nothing but the region which is separating P-type, N-type semiconductor in PN junction, which consists of immobile charge carriers. Now to just refresh once, because we talk about how voltage will be developed in the depletion layer, so just we try to refresh what exactly happens in the depletion layer, how immobile charge carriers are formed. We know that suppose if this is the layer which is separating P-type and N-type, and if this is a depletion layer, so this is a P-type semiconductor and this one is N-type semiconductor. Here we have plenty of holes and here we have plenty of electrons, and we know that when we start this process of diffusion, some of the electrons from inside, they'll diffuse to p side, and they are going to lose their energy to holes there, and these electrons, they will become negative ions, immobile negative ions. So these are called as immobile negative ions. Similarly, holes from the p side, they are going to migrate to n side, and they are going to lose their energy to electrons in n side, and of course they will become neutral, and these holes, they will act as immobile positive ions onto the right side, which is n-type layer. So we have such collection of positive and negative ions in depletion layer which does not take part in conduction. So this is our depletion layer, and of course what we are doing, as we know that bottom layer, it is completely covered with conducting layer, and this top layer, as you can see, it is not completely covered with conducting layer, but what we have done here in this case, we have left a small part open. So not fully covered, but small part is open so that the sunlight can penetrate into the depletion layer. Okay, and of course, as I told you, when we talk about photodiode and of course our solar cell, in both the cases there is conversion of light energy to electrical energy. But in our photodiode, it's a reverse bias diode, but in this case we are not applying any biasing. So we are not biasing it, we are not applying any external voltage to this particular solar cell. So still we are able to generate current. So that difference we have to understand. So as we can see, here is a depletion layer is formed at the junction of n-type and p-type semiconductors. As you can make out, this is our depletion layer. And when light energy from the sun, okay, sun rays, if we take our sun rays, fall on this solar, of course this is our solar cell, but what is solar panel or solar module, where there is collection of lot of such solar cell units. So once we make our sun rays fall on those solar cell units, then photons, okay, which act as small bundle of energy. So photons from sunlight, which act as small bundle of energy, and these bundles, they are going to have energy higher than the energy gap. So what is the energy gap? So in this case, we can make out that energy gap is nothing but EC minus EV. So here, generally photons which are associated with the sunlight, they'll have energy greater than energy of forbidden energy gap. Okay, so energy gap, and this energy gap correspond because here these photons are having high energy, they are highly energetic in nature. So what these photons are going to do, they are going to give energy to electrons and holes which are present in the depletion layer, or they are going to provide energy to these immobile positive and negative ions which are present in the depletion region. Then obviously what will happen now, electrons and holes, they'll move to higher level. So you'll have here again the process which is involved, it is called as generation of electron hole pair. So process involved is generation of electron hole pair. So here we have this process of generation of electron hole pair. And what is generation of electron hole pair? We know that suppose when we talk in terms of energy band diagram, we know that when we take our PN junction diode, so generally we'll take conduction band and valence band of P region higher than conduction band and valence band in N region. So this is the energy band diagram of PN junction, and of course this is our depletion layer. So this is our depletion layer, and we know that when we are leaving this, so this is our ECP and this is EVP, right? And this is the P region, P side of PN junction, and this is N side of PN junction. So this is our depletion layer where there are no charge carriers, and we know that if we consider P side, of course this is the ECN and this is EVN. These are conduction and valence band in N side. And one thing what we have seen here is once PN junction is formed, Fermi level it will become uniform throughout the PN junction, but still this Fermi level it will be closer to valence band in P side, and it is closer to conduction band in N side. And of course in N side we have plenty of electrons. So here we have plenty of electrons, whereas on P side we have plenty of holes. And once, of course, in depletion layer, we know that we have lot of immobile charge carriers. So what are those immobile charge carriers? Onto the N side, we have immobile positive ions, and onto the P side, we have immobile negative ions. Now, once we expose them to the sunlight, which consists of photons. So here we have photons, and what happens to these photons? These photons, they are going to be incident on those immobile charge carriers. And what is the process here? Here we have generation of electron hole pair, where generally what we are going to, of course, this energy difference is nothing but energy gap, and this energy difference is also equal to energy gap, and we are providing photons whose energy is greater than the forbidden energy gap. So obviously electrons which are present in the valence band, they are going to take that energy and they are going to jump to the conduction band, leaving holes, as well as giving rise to electrons in conduction band. So there is formation of electron hole pairs, and as you can make out that electrons move towards N-type, and similarly holes move towards P-type. Now, one important point is this movement, it will make them act as a battery. Okay, so that is nothing but generation of voltage. So this movement of electrons and holes, it is going to get us our electric current. So in order to understand, of course, this working more, what we are going to do, we are going to take what is the basic principle involved. And if you look at this figure, so what exactly is happening here? So whatever positively charged ions are present onto the N side of depletion layer, what they are doing, they are moving in this direction, and whatever negatively charged ions are there, they are going in this direction because of this sunlight, and because of this movement of immobile charge carriers, we are going to get current. And talking about the basic principle. Now, here, what we are going to observe here is the basic process behind photoelectric effect. So, there are three processes which are involved behind the photoelectric effect, which is going to take place in solar cell. So, first thing is, once we make our sunlight fall on PN junction or on the depletion layer, and this depletion layer, it is present at the junction of both p-type and n-type semiconductors. As we know that there is a movement of immobile positive and negative ions, so that is nothing but generation of charge carriers. So what do you mean by generation of charge carriers? When there is movement of immobile negative ions onto the p side, so it is going to give us electrons, whereas when there is movement of immobile positive ions onto the n-type, it is going to give us holes. So there is generation of electron hole pairs, and that is taking place because of our sunlight, and that sunlight, it is giving us photons. So because of absorption of photons in the material or near the junction region, we have generation of charge carriers. So this is the first step involved in solar cell. And the second one is, as you can make out, second step is subsequent separation of photo-generated charge carriers in the junction. So we'll see our figure also in the next figure. So what is the second point? Here we are saying that because of flow of charge carriers, there will be separation of photo-generated charge carriers. So electrons will start coming to one side, then holes will start coming to other side. So there will be separation of photo-generated charge carriers, and that too, it is taking place near the depletion layer or near the junction layer, which is separating p-type and n-type semiconductors of p-n junction. And then third step involved is collection of photo-generated charge carriers at the terminals of junction. Not only separation, of course, not only movement of immobile charge carriers, but these charge carriers, what they are going to do, they'll come and they'll form, okay, so voltage separation, or they'll form a battery. They'll act as battery because of collection of these photo-generated charge carriers at the terminals of the junction. So as you can, this point we can understand looking at this figure. So if we look at this figure, as you can make out, of course, this is our solar panel, solar cell. Okay, so p-type and n-type, and there is penetration of sunlight, and in order to make current flow, so what we are doing in this PN junction solar cell, we are connecting one load resistor. What is the role of this load resistor? It will help us in order to collect the current which is being generated in this solar cell. And as you can see in this second figure, So here, because of sunlight, so once we expose our solar cell to sunlight, of course, there will be movement of charge carriers. That is nothing but diffusion of electrons and holes. And what is the diffusion of electrons and holes? As I told you, across the p-n junction. So if I try to draw this p-n junction again, of course, this is the junction layer which is separating p-type and n-type. Right here, so we have lot of holes, and here we have lot of electrons. As I told you that when electrons from n side, when they migrate to p side, they are going to lose their energy to holes there, and here they'll form negative positive, they form immobile positive ions. Okay, we can say that as if they are forming terminals at the junction. And similarly, holes from the p side, they are going to migrate to n side, and they are going to lose their energy to electrons in inside. They'll become neutron and they'll form positive ions, immobile positive ions. Now once we expose them to sunlight, so what we are doing now, we are exposing them to sunlight, then what happens to these positive ions which are present onto the inside, they are going to move in this direction, and similarly or whatever immobile negative ions are collected onto the left side, that is p side of the p-n junction, they'll start moving in this direction. So that's why we'll say that there is diffusion of electrons and holes, okay, because they are moving. So now we can call them as charge carriers. Before that we are saying they are ions, but now because they are moving, we can say that diffusion of electrons and holes takes place. Now of course this is our energy band diagram of p-n junction here, and especially our solar cell. As you can make out, this is p side of p-n junction and this is n side of p-n junction. Okay, and here in this case, as we can make out that when we are exposing them to the sunlight, so what exactly is happening? And of course this photon, it is going to have energy, photon energy, which is coming from the sunlight. Its energy is greater than Eg. What is the Eg? Band gap. And what is the band gap? This energy difference is our band gap. Okay, similarly here, this is also band gap in inside of p-n junction, and we are supplying energy greater than Eg. So what we are going to observe here is, so these charge carriers, they'll absorb that energy and they'll go to their higher band, that is conduction band, and thereby resulting in formation of electron hole pairs. So because there is movement of charge carriers, so these, as you can make out from this figure, we have here positive ions, and these positive ions, where they are moving towards the p side because of this photons that are coming from the sunlight. And similarly, these negative ions which are present on the p side, they start moving towards the n side. Now this is our important figure which will help us to understand how there is generation of voltage across the terminals of the junction. So as you can see, those immobile positive ions, once they absorb photons from sunlight, they start moving towards the p side. Similarly, those immobile negative ions on absorption of photons, they start moving to n side. Now as you can see, there is collection of electrons onto the n side of p-n junction, and there is a collection, of course, all those negative charge carriers, they'll come and they get accumulated on the inside, and similarly all those positive charges, they'll come and they get accumulated on the p side, and at equilibrium, as you can make out, that there is a formation of voltage. So there is formation of open circuit voltage V0, which is going to generate current in solar cell. So that whole process we can understand in these 3 steps. So first what we are doing, so when photons in sunlight hit the solar panel, okay, and once they are absorbed by semiconducting materials such as silicon, then what is the second step which are going to happen? This is very important case. As I told you, electrons which are negatively charged, so they are knocked loose from their atoms, causing an electric potential difference. So currents start flowing through the material to cancel the potential, and this is going to give us electricity. And because of some special composition of solar cell, as I told you, when we make our solar cell, we just not make use of normal materials, but we make use of some special type of materials. And because of special composition of this solar cell, what we are going to observe here is all these electrons which are coming out of their atoms and which are giving their potential difference or voltage. They are made to flow in one single direction, and once they start flowing in single direction, and once we have a solar panel where there is collection of such solar cell units, and then once there is conversion of solar energy into that current, so what is our output? Our output is direct current. So here what is the output we are going to get from solar cell? Direct current. So we are going to get our electricity from solar panels because of those all solar cells making electrons move in one specific direction. So this is about the basic principle which is involved in solar cell. So this whatever we have discussed here, so all that it is explained in this PPT. As you can see here, when PN junction diode is exposed to light, then photons are absorbed and then electron hole pairs are generated on both p side and inside of PN junction. And what we are going to see here is across the junction, this electrons and holes, they are separated by a small distance, giving rise to voltage. And here what we are going to observe here is this electron hole pairs, they are separated by strong barrier field. Okay, so because they are separated, if you just go back to our figure and if you look at this fourth figure, in this figure we can make out that there is separation of course, charges, so which is giving rise to strong barrier field. So here electrons in the p side slide down the barrier potential and they'll move to n side. That is what I have shown in my figure. This is the figure. So all this negative ions which are onto the p side, they are going to slide towards the n side, and similarly all these positive charges which are onto the n side, they are going to slide onto the p side. So here what we are going to see here is here the electrons in the p side, they are going to slide down the barrier potential, they move to the n side, whereas holes in the n side, they are going to slide down and they'll move towards the p side. And here this point is very, very important. So when PN junction diode is open circuited, so what happens now? When it is open circuited, there will be accumulation of electron and holes on the two sides of junction, giving rise to this open circuit voltage, what we have seen in this figure. So here as you can see, there is collection of electrons and holes which is going to give us open circuit voltage. And if we keep a load resistance across the diode, then current starts flowing in the circuit. So we should have one load resistor being connected along with the solar panel so that there is flow of current, right? And here when we take VI characteristics of solar cell, we are going to talk about this short circuit current. Okay, and there are some parameters that are going to define a solar cell. So those different parameters we are going to see in our next slides. And what we have to understand here is, of course, these solar cells, if you talk about their applications, they are used in satellites and space vehicles. Okay, because for long duration of power supply, they'll help us in satellites and space vehicles. And also, as you know that these solar cells are not only just made up of silicon and germanium, but they are made up of this gallium arsenide, cadmium sulfide. We can also call them as direct bandgap semiconductors. So they are made with some special type of semiconductors, so they can be used in various device configurations. Now this is our solar module. As I told you, when we are making use of solar cell in order to draw electricity for household purpose or in companies or offices, not just solar cell will solve our problem. So what we have to do, we have to take collection of such solar cells. Now here if you see here, what exactly is solar module? It is also called as solar form. Okay, so it can also be called as solar form, right? And this solar module, it has got solar cell as basic building module. And what is the shape? It is in octagonal shape, and as you can see, it is a bluish black color. And each cell, how much voltage it is going to produce? It is going to produce around 0.5 voltage. So if we make use of about 36 to 60 such solar cells, and those solar cells, they are arranged in 9 to 10 rows, then if they are joined together, that is going to give a solar panel. So how this solar panel, solar module or solar form is made up of, we try to make use of, as you can see in this figure. So in this module, this is our solar cell, and here if we make out here in this solar panel here, we can take around 36 to 60 solar cells. And how many number of rows we can have? We can have around 9 to 10 rows, and they are going to form one such solar panel. And for commercial, whereas if you want to draw more current, we can go up to 72 cells also. And what we are going to observe is when we keep on increasing our number of cells, then our voltage, it can be increased. And when we talk about thickness of the solar panel, it is going to be around 2.5 to 4 centimeters. And all such solar panels together, they are going to form solar array. Now, in the end of this, we are going to just quickly have a glance at VI characteristics of solar cell. So this drawing VI characteristic of solar cell generally will do even in physics lab also. So there are some parameters that we are going to take out from VI characteristics of solar cell that is going to define a solar cell. So there are some parameters that will help us to differentiate between one type of solar cell to another type of solar cell. So in order to know this characteristic, as you can see, of course, this is VI characteristic where we have taken voltage on x-axis and current on y-axis. So there are certain parameters as you can make out. First parameter is ISC. It is denoted as ISC, and this parameter, it is called as short circuit current. So this parameter, it is called as short circuit current. And of course, how we are going to measure this current? By short circuiting the terminals of solar cell. And then next we come across one more parameter which is called as open circuit voltage, which is given as VOC. And how we are going to measure it? We are going to measure it when there is no load. So when there is no load connected in the circuit, so with no load, we are going to measure one voltage, and that voltage, it is called as open circuit voltage. And apart from that, we have our PM, which is maximum power, and IM is maximum current, and VM is maximum voltage. And this all of them, they occur, this maximum power, it is going to occur at the bend of characteristic curve. As you can see, there is a bend. So at this bend, we are going to calculate our maximum power PM, and this maximum voltage VM, and then maximum current IM. So for that, in order to calculate all this of solar cell, first we need to draw voltage characteristic curve. As you know that here, as I told you, this ISC is our short circuit current. So first what we are going to do, we are going to short circuit the terminals, and then we are going to measure current. So that current value, it will be maximum. Okay, so what do you mean by short circuiting the terminals? When voltage is 0. So first what we are going to do, we are going to put voltage 0, and we are going to measure what is the flow of current across the solar cell. That current, it is called as short circuit current, and that current, it is of maximum value. Okay, so now starting from that, when we keep on now increasing the voltage, what happens to this short circuit current? It will keep on decreasing, and then we come to this point. So here, in order to increase this voltage, what we are going to do, this load value, it is going to decrease. And here, when there is no load in the circuit, there is a maximum value of voltage. That voltage, it is called as open circuit voltage. And once we get our VI characteristic curve like this, using this curve, we are going to make out what is the maximum power, maximum current, or maximum voltage that can be drawn from VI characteristic curve of a particular solar cell. So what we are going to do, as you can see, there is a bend in the characteristic curve. At this bend, I am going to calculate this maximum power, and corresponding to this bend or this maximum power point, corresponding current, it is called as maximum current, and corresponding voltage, it is called as maximum voltage. So just quickly, if we try to look at the different parameters, so various parameters of solar cell which can be determined from VI characteristic. First parameter is our short circuit current, which is given as ISC. Then we have our open circuit voltage VOC. How we are going to get a short circuit current? By putting voltage 0, and how we are going to get open circuit voltage? By connecting no load in the circuit. And there is one factor called as fill factor, which is denoted by FF, and of course in the end we have our efficiency. And rating, whether a solar panel is good or bad, it is more effective or not. So that rating of a solar panel, it depends on these parameters. So just if we try to quickly define these parameters, as you can see here, what is short circuit current? So this is the current which is flowing across the solar cell when voltage is 0. So when we keep our voltage across the solar cell zero, whatever maximum current is flowing across the solar cell, it is called as short circuit current, or when the solar cell is short circuited, and of course as I told you, this current will be maximum, which we have seen in VI characteristic. Then after that we have our open circuit voltage, and this is the maximum voltage available from the solar cell. And this occurs when there is no load, or this occurs when there is zero current. And this circuit voltage, it corresponds to amount of forward bias on the solar cell due to biasing of solar cell junction with the light. Then coming to third factor, which is fill factor, which is simply given as FF. And as you can see, it is in conjunction with this open circuit voltage and short circuit current. And generally how it is taken, it is the ratio of maximum power from the solar cell to the product of VOC and ISC. So how we'll get that maximum power from solar cell? So this point is maximum power. So then maximum power from the solar cell. So we have a ratio. In the numerator we have maximum power, which is taken at the bend of VI characteristic. In the denominator we have product of open circuit voltage and short circuit current. And in the end, one more parameter is efficiency, and this efficiency is most commonly used parameter in order to compare performance of different solar cells. And how this efficiency is defined, it is defined as ratio of output energy from the solar cell to the input energy from the sun. So how much energy we are giving to the how much energy we are drawing from solar cell. So that ratio is nothing but efficiency. And in addition to drawing this performance of solar cell, and this efficiency, it is going to depend upon the sunlight parameters, like what is the spectrum, what is the wavelength of sunlight falling on the solar cell, and what is the intensity of incident sunlight, and also what is the temperature of solar cell. Now quickly in the end, we are just going to have glance at different materials that are used in making of solar cell, and generally what type of materials we will use in order to make solar cell. We will make use of materials which are having band gap closer to 1.5 electron volts, and commonly used materials are of course our silicon, then our compound semiconductors like gallium arsenide, then cadmium selenide, and then of course this alloy which is made up of copper, indium and selenide. And when we are selecting materials for solar cell, what should be our criteria? First thing is, of course, it should have band gap which is falling between 1 to 1.8 electron volts, and it should have high optical absorption. Whatever charge carriers are present in that material, they should absorb photons quickly. They should have fast response time. So that is nothing but high optical absorption, and also they should have high electrical conductivity. And of course, this material, it should be like available abundantly, so that cost used in order to make solar panel is low. And of course, these are some of the advantages and disadvantages of cell, because we are making use of sunlight, no pollution, it will last for a long time, and there is no maintenance cost. And coming to disadvantages, of course, material, they are in abundance, but there will be high cost of installation. It has low efficiency, and of course, because our output, it depends upon sunlight. So days, during night, when there is no sunlight, we are not going to draw current. So this is one of the disadvantages of solar cell. I hope there is clear understanding about solar cell from this video. I'm going to end my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.